Hi, my name is Valentin and I'm presenting the work from me and my co-authors Andreas, Danny, Oz and Marc called Long Horizon Multi-Robot Rearrangement Planning for Construction Assembly, which was recently published in TRO. We'll first have a look at the problem that we're trying to tackle here and why it is hard and what the difficulties are. So, in this work we're looking to build or assemble a given final design with a given set of robots and some initial configuration of parts. Examples of such robots and some examples of final structures can be seen on the right. The structures that we used in the demonstrations are a tower, where the construction cannot be very well parallelized due to precedence constraints, and a wall, a pavilion, and a well, where the robots can work well in parallel. The robots we used are mobile robots of different topology and a crane in the examples. I'll also show a video in the end where we used multiple pandas arms. Our goal is to make good use of the robots, so essentially we want all robots to be in use all the time. Ideally, we would like to minimize the make span, but we'll settle for a low make span for now. This description hides some difficulties. We first need to find a feasible assignment of parts to the groups of robots. And then we also need to compute a path that fulfills the assignment. So there might be quite a few constraints on the possible path and assignments. We would also like this approach to scale to many robots. So if we simply do joint planning, that scales badly with an increasing number of robots. So we want to do something different, namely we want to exploit the factored nature of the problem. So how are we actually tackling the problem in this work? The core insight here is that there are very little extremely long-term dependencies over the whole construction horizon. This means that what we can do is to separate the complete problem consisting of all parts and all robots into a sequence of problems containing only few robots and a single part at a time. And we then solve these subproblems sequentially while considering the previously found path as fixed. This core idea requires two main algorithmic components to work. First, a way to choose robots and parts that make up a single subproblem, and secondly, a way to solve this task and motion planning subproblem. The first, on the left, we simply do greedily in this work, meaning that we use a user-defined heuristic that we optimize over to obtain a group of robots and a single part. We then try to find a valid action sequence for the involved robots, which could be a pick and place sequence, or it could involve a handover. If we can't find one, so if it's infeasible with a group of robots for a specific part, we backtrack. Solving a subproblem then works by first sampling valid keyframes for the task and motion planning subproblem. So for example, we try to find a handover pose. We then compute a path using spacetime RRT and post-process the path by smoothing it and shortcutting it. But what is STRRT? Spacetime RRT enables us to take the previously planned path into account by extending the configuration space with a time dimension. We then simply do bi-directional RRT in spacetime with some special sampling procedures to take the constraints arising from the time into account. To plan a full action sequence, we then repeat this for each action, which is illustrated at the bottom. But does all of this actually work? I'll first show a video of two arms stacking some boxes using the approach I just talked about, and then highlight some results from the paper. The algorithms that are presented was used to compute the path that is executed here in the video by the robot's open loop. The video is not sped up, so this is real time. In the video, the robot goes to an intermediate pose to not block the next action by the other robot. This intermediate movement was made obsolete in follow-up work. Now, some more examples of produced schedules from the algorithm. On the left side, you can see a schedule for the pavilion consisting of 152 parts for 8 robots, and on the right side, you can see that the approach also works with more complex sequences that in this case require interaction between multiple robots because the tower cannot be stacked at as high by only the mobile robots. Finally, I briefly want to talk about scalability and what happens when we add more robots to the same problem. On the left side, we can see the speed up of the execution time that we get by adding more robots. As expected, the relative execution time hits a wall at some point, so we get diminishing returns of the speed up, because multiple robots cannot parallelize the problem even more. On the right side, we can see that the computation time of the approach scales more or less linearly with an increasing number of robots. This is mainly due to the increasing congestion when dealing with more robots. To summarize, we presented an approach to plan an assembly sequence with many robots and for long horizon problems, and we demonstrated the approach in simulation and on a real robotic system. Our approach works by exploiting the factored nature of the problem. In the future, we'd like to implement this approach in the actual design loop of buildings. We would like to look at active support to stabilize intermediate structures, and we recently started looking at optimality for the problem that we talked about just now. Thanks.